Hello, everyone. Today's lecture, we will continue on what we started in root locus topic. So let's try to solve this example. Basically, we need to solve the root locus for this one. So the first thing that we will do is to do the pole zero mapping. Then identify where are the zeros and the poles. So we have a zero at s equal -3. Then the poles location at 0, -1, -2, and -4. Then identify these poles and zeros on the S-plane mode. So there is a pole at s equals 0. There is a pole at s -1, another pole at -2. There is a 0 at -3, then a pole at -4. That's the pole zero mapping. This is the first thing that we identify them. Then, as we discussed last lecture, let's identify the roots Lucy segments. So in order to determine the segments, the first thing, start counting from right to left. The odd number will be considered as a segment. The even number will not be counted as a segment. And then keep in mind, count the zeros and poles, both of them. Let's start from the 0 here. 0, it's the pole at 0. Here now, the sum of the poles and zeros is 1. Then since 1 is odd number, therefore the region between 0 and -1 is considered as a segment. Then after that, once we reach the -1, you will see that the number of poles and zeros is even. Therefore, the region between -1 and -2 is not counted. Then when we reach -2, we can conclude that the number of poles and zeros is 3, which is odd number. Therefore, the next region is considered as a segment. Then the region between -2 and -3 is a segment. Then when we reach -3, we will realize that, or the total number of poles and zeros is 4. Then the between -3 and after that is not considered as a segment. Once we reach -4, this is not counted as a segment. Then once we reach -4, then you can see we have 1, 2, 3, 4, 5 poles and zeros. This is number 5 is odd number. Therefore, then we can say after -4, it's considered as a region. Then by looking at it, we can say the number of poles or the regions, these segments are the only place for the poles on the real axis to move. Then we can say the -4 pole, this pole, it will be going to either 0 or plus or minus infinity, but it's allowed to move only to the left region. Therefore, it will go to the negative infinity. That's the first thing about the pole -4. Then look at the pole -2. It goes to the -3, 0. Then that's good. We can say the -2 will go to the 0, -3. Then that's it. There are two remaining things, which is 0 and -1. 0 and -1, they will go the opposite of each other. Until reaching to the critical point, after that, they will go up or down, or they will be they have a possibility to go this or this, or the possibility to go this way or this way. So how can I know that? By determining the centroid and the angle of asymptotes, or centroid of asymptotes and angle of asymptotes. How can we find them? We will do the formula that we did last lecture, which is basically to find the centroid of asymptotes. Basically, it is the sum of poles minus the sum of zeros divided by number of poles minus number of zeros. So the sum of poles, basically we can say 0 minus 1 minus 2 minus 4 minus the sum of zeros -3 divided by number of poles, which is 4 minus number of zeros, which is 3. Then we can say 0 minus 1, -1, -2, -4, which will be -7, -7 plus 3, which is 4, -4. Then -4 divided by 4 minus 1, which is 3. Then it will be -1.333. As a result, we will look, or we will say that the centroid will be at -1.333. This is the sigma. Let's calculate the angles now. To calculate the asymptote angles, we will say phi or psi a, whatever symbol that we call, 2q plus 1 divide by n minus m, which is 4 minus 1, which is 3, times 180 degrees. Then we will substitute q from 0 to 4, because basically q, we used to substitute q from 0, 1, 2, until number of poles minus 1. So we have number of poles is basically 4 minus 1, 3. Therefore, we will possibilities of q 0, 1, 2, 3. Let's substitute q0 first. So when we substitute q0, this yields phi a as 1 over 3 minus 180, which is 60 degrees. The next thing here is when q equals 0. When q equal 1, when q equal 1, this will be 3 over 3, which is 1. Therefore, it will be 180 degrees. After that, when q equal 2, this yields the angle to be 2 times 2, which is 4, plus 1, 5. 5 divided by 3 times 180 will be 300. Then if q equal 3, we will see that 3 times 2 will be 6, plus 1, 7. 7 times 180 divided by 3. This yields to be another 60. So as a result, we can say the 300, let's say 2 times 3 is 6, plus 1, 7. Yeah, just 160. Or I would say 7. 7 over 3 times 180, which will be 7 times 60. 6 times 7, 420. Then subtract 360 degrees. It will be 40. It will be 60. Just like what I said, 60 degrees. So when we look at it, the 300 or 180 degrees, it's already been achieved here and here. The angle, 180 degrees. Then the next thing is, when we look at these two poles, we have angle of 60 degrees, angle of 300, or I would say negative 60 degrees. So I would say like angle here, 60, negative 60. But we need to keep in mind there's an asymptote centroid. So asymptote centroid, basically, it's located at negative 1.33. So here is negative 1.33. Then let's put the asymptotes with angle plus 60 degrees and minus 60 degrees. Then, when these two poles reach the points, then they will be moving like this. Okay? Now, with this situation, we already almost done with the root locus of this plot, but there is one missing information left. Once we found it, everything will be good, which is the other information that we need to keep in mind. What are the intersections here? There should be an intersection here, intersection here. Okay, what are those intersections? And what's the value of k? So we need to determine what's the value of k and what are those intersections. In this situation, we need to make sure that we don't want the value of k to be exceeded. So here I would say when k equals 0, all of the poles are location here. When k equal 1, they are moving to, etc., until reaching to the points. If it goes toward the infinity, the poles, these poles will go toward infinity, and this pole will go toward the 0. This pole will go toward the negative infinity. However, since our concern is the system stability, therefore we need to make sure to identify what's the points or the critical points that for k to make the system marginal stable. So if the poles, these two poles, reaching the marginal stable, then after that the system will be unstable if we keep increasing k. So how can we find the marginal stable k? Basically, in order to identify this, we need to do the multiplication or look at the denominator to find the characteristic equation. So I would say the denominator d of s, it is actually s plus 1, s plus 2, s plus 4. Now let's do the multiplication to find the characteristic equation, which is here s squared plus s. Then here s times s, s squared plus 2s plus 4s, 6s plus 2 times 4, which is 8. Then the next thing is to do the multiplication for these two, which will be s times s will be s power 4, s squared times s squared, s power 4, plus s squared times 6s, 6s power 3, then plus 8s squared, then let's deal with s, plus s cubic plus 6s squared plus 8s. Then after that, we can say here's cubic, cubic, square, square. Then the characteristic equation will be s power 4 plus 7s cubic plus 8 plus 6, which will be 14s square plus 8s. Now, the next thing is to do the Rauter-Hurwitz. Oh, there is k. I need nothing to do this correction. I apologize. Before doing this, we need to do the characteristic equation for the closed loop. So let me do it again. Sorry for the inconvenience. I will assume this as g of s. So the closed loop transfer function c of s over r of s equals g of s divided by 1 plus g of s. Then it will be k s plus 3 divided by s, s plus 1, s plus 2, s plus 4. Then divide by 1 plus k s plus 3 divided by s, s plus 1, s plus 2, s plus 4. Then after that, let's do the shortcuts or to do multiply by the denominators of these two. Then after that, when we simplify, it will be k s plus 3 divided by s, s plus 1, s plus 2, s plus 4, plus k s plus 3. Then look at the characteristic equation, which is the denominator here. This is the characteristic equation. Now, let's do a simplification. So as we mentioned, it's s squared plus s times s squared plus 6s plus 8 plus ks plus 3k. Then let's do more simplification, which is s squared, s power 4 plus 6s and 7s cubic plus 8s plus 6s cubed. So it will be 14s squared plus 8 plus ks plus 3k. That's the characteristic equation. Then in order to find the range of k, to make the system stable, we will do the Routh-Hurwitz stability. Basically, here is s power 4, s square, s cubic, then s square, s power 1, s power 0, then put the coefficients. So here is 1, 7, 14, 8 plus k, 3k, and there is one other image, so this one will be 0. Then we need to do the roots, or say like Routh-Hurwitz. So let's find the element here. I can call it this as B1, B2. Here's B1, here's B2, here is C1, C2, here is D1. So let's calculate first thing B1. B1, it is the determinants 1, 14, 7, 8 plus k divided by 7. So it will be 8 plus k minus 14 times 7 divided by 7. So 14 times 7, which will be 98. Then 8 minus 98, which will be 90. So it will be k minus 90 divided by 7. This is the value of B1. However, let's calculate the value of B2. It will be basically, we will look at this part. So it will be the negative. Here is, oh, I missed the negative sign. So it will be 90 minus k. Because there's a negative sign right here. Okay. After that, we will do for B2, which is the negative, the determinant 14, 3k, 8 plus k, 0, divided by 8 plus k, and the answer will be 3k. Now I can substitute them here. So I will substitute this one, 90 minus k divided by 7. Here is 3k. How about to calculate the other c's, which is we have C1, C2. To calculate C1, C2, and D1. So in order to calculate C2, basically, those are zeros. Therefore, C2 will be for sure 0. The next thing to calculate C1. How about to calculation of C1? It will be the determinant of the above, this, minus the determinant of this. So it will be negative the determinant of 7, 8 plus k, 90 minus k divided by 7, 3k, all of them divided by 90 minus k divided by 7. So let's substitute them. This yields to be negative 7 times 3, which is 21k, minus 90 minus k divided by 7 times 8 plus k, all of it divided by 90 minus k divided by 7. Then what we can conclude, let's try to distribute the division. Here is negative 21 divided by k divided by 90 minus k, all of it times 7. Then minus minus will make it positive, plus 90k, 90k divided by 7, plus 8 plus k. Then let's simplify it more by saying 7 times 21, which is 147, negative 147k divided by 90 minus k plus 8 plus k. This is the value of C1. How about to calculate D1? In order to calculate D1, look at this diagonal element divided by C1. So basically, we would realize that D1 equals 3k, the net resultants. Now, in order to make sure the system is stable, let's look at the first column. And we need to make sure the first column is larger than 0 or positive. So I will say that 90 minus k divided by 7 must be larger than 0. This yields k is less than 90 degrees. That's the first observation. The second observation, when we look at 3k, so 3k must be larger than 0, therefore k larger than 0. Okay, then the last observation, which is regarding to the C1. We need to make sure that C1 is larger than 0. Then let's look at C1 and say we need this part to be larger than 0. So negative 147 divided by k divided by 90 minus k plus 8 plus k larger than 0. Then let's try to solve it to figure it out. Move it to the other side. This part, it will be 8 plus k larger than 147k divided by 19 minus k. Then do the cross multiplication for this. This yields 8 plus k times 90 minus k must be larger than 147k. Then let's do the multiplication. 8 times 90, which yields 720. 720, then 8, let's do it. 8 times 90, 720, minus 8k. Then the next thing is to look at k minus 90. So plus times 90, which is plus 90k. Then the next thing, which is k times k, which is k squared, negative k squared, must be larger than 147k. Move 147k to the other side. This is a quadratic equation. Then it will be, and we can move k squared to the other side as well. So I would say the way that I like, make it 0 here, then negative 720 plus 8k minus 90k plus k squared plus 147k. Let's simplify the case. So we have 8 minus 90 plus 147. This yields 65. So here we have 0, negative 720 plus 65k plus k squared. This is a quadratic equation. Let's try to calculate the roots of k's. How to calculate the roots of k's? Basically, we will use the general formula, which is k equals to negative 65 over 2 plus minus the 65 squared minus 4 times 1 times negative 720. Then let's calculate the roots. So 65 or like 4. 65 squared times 65, which is 4,250. Negative 65 divided by 2 plus minus the root 4,225 minus 4 times 720, which will be, here's 9 minus will be positive 2,880 plus 4,225. Then let's do the root of it. Then let me figure out how to find the roots. Okay, so the square root of this number will be 84 something. So it will be negative 65 divided by 2. Let me write it here. It will be negative 65 divided by 2 plus minus the 84, I would say 84. So 65 plus negative 65 plus 84, which will be 19. divided by 2, it will be 9.5. That's the first root. The second root, which is negative 65 plus, or I would say, yeah, it's minus 84. This will be 149 divided by 2. Then it will be 74, negative 74.5. Then as a result, I can write the k's here, like it will be k minus 9.5. Then the other k minus will be positive 74.5, all of them less than 0. This yields, we can take the first half, then the second half, k minus 9.5 less than 0, therefore k will be less than 9.5. That's one condition. Then the other one, k plus 74.5 less than 0, therefore k less than 74.5. So I would say, let's look at the negative numbers of k. We will look at the positive numbers. Therefore, we have k less than 9.5 and k here less than 90. So the way I would say, assume here k will be bounded between 0 to 9.5 degrees, 9.5, let's say. So we can say at k equal 9.5, it will be marginal stable. This is the critical. So let's calculate the characteristic equation, or to calculate the poles when k equal to 9.5. Where are the location of the poles? We have a fourth order system, so it will be kind of difficult to determine this spot. Let me do it. So let's do s power 4 plus 7s cubic plus 14s squared plus 8 plus 9.5, 8 plus 9.5, which will be 17.5, s plus 3 times 8.5, not times 9, 3 plus times 9.5, which will be 76. That's the characteristic equation when we have a marginal stable. So anyway, here we determine the value of k, which is 9.5, that will make the system unstable. Now let's go to another example. I know this example is cost us a lot of time, but I would say just to prove the concepts, that's how we are doing. Then in this situation, once we find k and s, the problem will be done. Everything is good. The next thing, before going to the next example, I would like, just let me erase this because I don't have enough room. After that, I'm gonna discuss the what we will do next. Okay, I'm almost done. Now, for the next example, let's assume we have the following transfer function. S cubic, s squared to s. Assume we have this block diagram, which is 1 over the open loop transfer function. It is 1s, s plus 1, s plus 2. This is the open loop transfer function, and we would like to put the controller gain, k, then in the closed loop, here is positive, negative. We would like to apply the root locus. So with this example, in order to plot the root locus, we will look at the first thing, the open loop poles and zeros. Here, we don't have zeros, we have poles. The poles location at s equals 0, -1, -2. So let's do the plots. In order to do the plots, the first thing that we need to figure out is to identify where is the poles and the zeros. Here is a pole at 0, pole at -1, pole at -2. Let's identify the segment between 0 and 1. This is considered as a segment. Between -1 and -2, this is not a segment. While between -2 and -3, this is considered as a segment. Then we will say the -2 will go toward the -infinity, while 0 and 1 will collapse with each other, or will be, I mean, I would say like collide, then they will be go to the plus minus infinity. So how can they go? We need to calculate the centroid first. To calculate the centroid, sigma A will be the number of poles, or the sum of poles, -2, -1, plus 0, minus the zeros, which is 0, number of poles, 3 minus 0. This will be -3 divided by 3, which is -1. How about the angles, phi or psi, which is 2q plus 1, divided by number of poles minus zeros, which is divided by 3, times 180. This yields to be 360. This is to be, I'm sorry, 60 degrees, 180 degrees, and 300 degrees. 300 degrees is already been manipulated, already manipulated here. 60 degrees and 300 degrees, or I would say 300 is the same as -60. Then we will can say here is sigma. Then they will be moving this way. Now the next thing is to identify at what value of k there will be a marginal stable, and what are the location of that. So in order to identify that, let's find the first thing, the closed loop transfer function, then to find the characteristic equation of it. So the closed loop transfer function, if we assume this is g of s, it will be as 1 or k g of s over 1 plus k g of s. This is c of s over r of s. Substitute g of s with its equation, which is we have k over s plus 1, s plus 2, divided by 1 plus k over s plus 1, s plus 2. Now let's multiply s plus 1, s plus 2, divided by s plus 1, s plus 2. I didn't have enough room here. Let me substitute it right there. Once we do the substitution, it will be k divided by s plus 1, s plus 2, plus k. In other words, we can simplify it to be k over s cubic plus s plus 1, s plus 2, which make it, I think, 3s squared, then plus 2s plus k. So the characteristic equation is the roots, or basically is the root of this numerator. Then the next thing, we need to identify the j omega axis. What's the value of k? What's the value of s? That will be here. Look at the characteristic equation. That's the characteristic equation that we have. Then the next thing is to do the Routh-Hurwitz criteria. In order to do the Routh-Hurwitz, the first thing, identify, put here 1, 3, 2, k. Then in order to find the other elements, or to identify this one, basically you can say -1, 2, 3k divided by 3 will make it as -k2, 6 minus k divided by 3, and that's what we got here. Then here, the element will be 0 because this column is 0. Then the next thing, when we do to find the next element, basically, we will look at these 4. So it will be -3k, 6 minus k divided by 3, 0. All of them divided by 6 minus k divided by 3. This yields k. So that's how we get k. After that, in order to make sure the system is stable, we need to have these conditions met, which is k larger than 0, 6 minus k divided by 3 larger than 0. Therefore, this yields k less than 6. As a result, in order to make the system stable, k must be bounded between 0 and 6. Then we will say it will, or here the system will be stable. This is the stable region. The system will be marginal stable at the borders when k equals 6. Then we can go back here and say k equals 6 will yield the problem, or will go, or this is the critical k. After k, if you increase k more than 6, the system will be unstable. So when you do your controller design, you need to keep in mind, please don't make sure the value of k will not be exceeded. So don't exceed the critical value. Don't increase k more than 6. The next thing is to calculate the s. Where is the location when the value k equals 6? Basically, you will substitute k here equals 6, then try to calculate the poles. So how about when we calculate the values? The crossing points at the imaginary axis can be found by solving the auxiliary equation obtained from the row s squared. So what we will say is, look at the row s squared. This is considered as 3s squared plus k. 3s squared plus k. Substitute k as 0, which will be 3s squared plus 6 equals 0. This yields s squared equals to be 6 divided by 3, which will be negative 2. Therefore, s equal plus minus root of negative 2, which is s equal plus minus j root of 2. Then we can say plus minus j root of 2. Substitute it here. S equal plus minus j roots of 2. Those are the critical points that we would like to avoid, or when we do the controller design, or these are the intersections. Okay. So the thing which is how to determine the points in case if, for example, or another way or alternative approach to determine the value of k other than using the router, which basically we will say, since we are in the pole 0 in the complex mode, which is S-plane mode, then the intersection here, this is j omega intersection. When s equal j omega, this at this point, this will reach to the marginal stable station. Therefore, we will go to the characteristic equation, substitute s as j omega. Then after that, we have two unknowns, k and omega. Find them. Those will be k critical and omega, which is when the system will be marginal stable. So substitute s equal j omega, s j omega, s j omega, s j omega. This yields to this one, j omega cubic plus j omega squared plus 2j omega plus k. Now, j omega cubic, it will be j cubic omega cubic. So which will be the square root of negative 1 also square times j. Or you can say j squared times j, which is square root of negative 1 times j. Then I would say j cubic equal negative j. Then the next thing about j squared equal negative 1. Therefore, we can simplify it to be negative j omega cubic plus, or it will be minus 3 omega squared, because j squared will be negative 1, plus 2j omega plus k. Then look at the imaginary parts, put them together, put the real parts together. Then when we put the real parts, it will be k minus 3 omega squared plus j. Then look at the imaginary parts. We have 2 omega, negative omega cubic, 2 omega minus omega cubic. All of them equal 0. Therefore, in order to calculate the critical point, this yields to make the imaginary parts alone equal 0, real parts alone equal 0. We have two equations, two unknowns, two equations. That's great. Let's try to figure out to calculate omega. To calculate omega, we can say it is omega 2 minus omega squared equals 0. Therefore, omega equals 0, and omega equal plus minus j square root of 2. The next thing is to calculate the values of k. Let's calculate the values of k. We have three possibilities of omega. Then we can say k equals 3 omega squared. If omega equals 0, this yields k equals 0. If omega equals plus minus j root of 2, this yields k to be 2 times 3, which is 6. So I would say we have two possibilities, this one and this one. Which one should I use? When we can say the intersections, when k equals 0, we have one pole here. When k equals 6, we have a couple of poles here at plus minus 2. And this is k equals 6 plus j, here's j2 minus j root of 2. And this is the same as what we used to get, and the same thing that we did in the plot. In the plot, we identified this. This is the intersection point, -1, and this is j root of 2, j negative root of 2. I think there is a root of 2, j negative root of 2. So an intersection at k equals 6. K equals 6. When k equals 0, these are the intersections. And this is the same thing when the same thing like what we did in our analysis. Here's the root locus using MATLAB. How can I perform the root locus using MATLAB? Look at the open loop transfer function, the open loop transfer function that we have here, which is without the value of k, which is 1 over s plus 1, s plus 2. Let's try to make sure write it as a polynomial. Then it is 1 over ss, which is s squared plus 3, or it's s cubic plus 3s squared plus 2s. Then we will, in order to do it in MATLAB, we will define the numerator first as the vector of 1, the denominator as the vector of 1, 3, 2, and 0. Then identify the system G as transfer function of numerator denominator. That's what we did before. Then in order to do it, to do the root locus, we will write R locus, L-O-C-U-S of G. Once you do it, it will give you this plot. That's how we can use it using MATLAB. Let's do another example. Consider the system with the following characteristic equation. With this characteristic equation, we can say that how many poles do we have in the open? This is the open loop transfer function. How many poles? 0, -2, -3. How many zeros? -1. Then the next thing is when we do these things, this is the G of S because it's 1 plus k G of S. That's how we identify this, the open loop transfer function. Then let's do the pole zero mapping and calculate the sigmas and asymptotes. The pole and the segments as well. Here is the pole zero mapping. We have a pole at 0, a pole at -2, a pole at -3, and 0 at -1. Then the next thing, let's identify the segments. So between 0 and 1, since odd number, that's it. After -1, it is even number. After -2, it's odd number. Then that's it. So we can say between 0 to -1, the pole at 0 will move to -1. So that's the first observation. The second thing, between -2 and -3, they will go in different ways. So what should I do? The first thing, let's calculate the centroid. Then after that, we will calculate the asymptotes. To calculate the centroid, sigma A, which is the sum of poles 0, minus 2, minus 3, minus the sum of zeros, which is negative 1, divided number of poles minus zeros. This yields to be negative 4 divided by 2, then it is negative 2. So the centroid here will be negative 2. After that, let's calculate the asymptotes. The asymptotes looks like, or how to calculate it, basically phi or psi, whatever we call it, of the asymptotes, it will be 2q plus 1 divided by, is it 2q or 3q? Let me double check. The asymptote 2q plus 1 divided by 3 minus 1 times 180. Then it is 2q plus 1 divided by 2 times 180. Substitute, we have 3 poles. Substitute q equal 0, 1, 2. At q equals 0, it will be 0, 1, 2, which will be 90 degrees. At q equal 1, 3 divided by 2, 180, which is 270 degrees, which is the same as negative 90 degrees. Then at q equal 2, which is will be another 90 degrees. So we have the asymptotes, 90 degrees, negative 90 degrees. Then I'll select the asymptotes angle. Then we have 90 degrees and negative 90 degrees. How can this happen for 90 degrees and negative 90 degrees? Basically, we will say that these poles will go to this way, then they will move like this. Then this pole will go this way, this pole will go this way with the asymptotes. Okay, that's how we do the root locus. Let's look at the graph. This is very similar on the graph. Is there a way for the system to be unstable? We can say the system is marginally stable at k equals 0, while otherwise, most likely, if until k equal infinity, the system will be stable. So when k larger than 0, the system will generate a stable. We don't need to do the Routh-Hurwitz or the other thing. Everything should be far all right. Another example. Consider this characteristic equation, which is basically we have, this is g of s, so the poles and zeros. The poles, s equals 0, negative 2, then we have negative 4 repeated. How about zeros? Zeros actually equal to negative 1. The first thing, let's do the plots. So we have a pole at 0, pole at negative 2, pole at negative 4, and another pole at negative 4. Then we have a 0 at negative 1. Let's calculate the segments. Here is the segments. Then between 0 to negative 2, it's not as considered as a segments, while here this is a segments. Then here, this is a segments. So what we're gonna do, basically, we can say the first thing is the pole between 0 and negative 1. 0 go to negative 1. Then we have negative 2, negative 4. Then we will say that negative 2 and negative 4, there's an area here. Then there's one pole will go toward the infinity. So we have a region of 3 poles. One of them will go toward the negative infinity. Then the 2 remaining, we need to identify them by calculating the centroid and calculating the angles, the phi angle. So how can we calculate them? Basically, let's calculate the centroid. Sigma A equals to be sum of poles negative 4, negative 4, negative 2, plus 0 minus the zeros minus negative 1 divided by 4 minus zeros. So the answer will be negative 3. So there's at negative 3, there's an asymptote. After that, we need to identify the angles for each one. So phi A or phi of the asymptotes will be 2q plus 1 divided by n minus m, which is 4 minus 1, which is 3 times 180 degrees. This yields phi A equals, we substitute 0, 1, 2, etc. We substitute this yields 60 degrees, 180 degrees, 380 degrees. So as a result, we can say one of the poles will be 180 degrees. That's why it goes toward the negative infinity. Then at -3, there is an asymptote like this way. First one, the first pole will go this way. Second pole goes this way. So as a result, we can say there is the system can be unstable for a some set value of k. So we need to identify what's the value of k and what's the value of omega here. Look at the characteristic equation. Then we need to identify what are the intersection points. The characteristic equation, when we simplify it, it will be s plus 2, s plus 4, all of it square, plus k, s plus 1 equals 0. Then after that, we will do the substitutes s equal j omega. So we can find the characteristic equation. So let's the marginal stable things. So let's substitute j omega. This yields j omega plus 2, j omega plus 4, all of it squared plus k, j omega plus 1 equals 0. Then let's try to identify it. J omega, so it will be j omega, j square omega square plus 2 j omega. Then here we have j square omega square plus 8 j omega plus 16 plus k j omega plus 1 or plus k equals 0. Then let's simplify it more. Let's do more multiplication. J square and j square will be j power 4 omega power 4 plus 8 j cubic omega cubic plus 16 j square omega square, then plus 2 j cubic omega cubic plus 2 times 8, which is 16 j square omega square plus 32 j omega plus k j omega plus k equals 0. Then let's try to group them together. So the highest order, j4, j power 4, omega 4. Then let's look at the cubic, try to sum them together. Here is a cubic, here is a cubic, no more. 2 plus 8, which is 10. J cubic, omega cubic. Then let's group the squares together. So here's 16 j square, 16 j square, no more. So it's 16 plus 32 j square omega square, then plus a group the j's together, which is 32 plus k. So it will be plus 32 plus k j omega plus k equals 0. Substitute j square as -1, j cubic as negative j power 4 as 1. This yields to be omega square plus, or here it will be minus 10j. Let me do it again. It will be omega power 4 minus 10 j omega cubic plus, or it's minus 32 omega square plus 32 plus k j omega plus k equals 0. Now let's group the real parts together, the imaginary parts together. This yields to be, let me write it down here, omega power 4 minus 32 omega squared plus k plus j of negative omega cubic plus 32 plus k equals 0. Then we have two equations, omega power 4 minus 32 omega squared plus k equals 0. Then the other thing, negative omega cubic plus 32 plus k equals 0. So these are two equations, but these are two nonlinear equations. I think it's hard to find, but the overall idea, we will calculate omega, calculate k. We will say that these two, where the system will be marginal stable. Once we found them, we will say the intersection is this point. Let me call it as omega star, k star, j omega star, negative j omega star, and when k equal to k star or critical. So that's it. Again, the root locus using MATLAB, basically the command rlocus. Okay. Here's, we do the transfer function, coefficient of the denominator, numerator, and denominator, then root locus of the system. So what we, again, what's in summarize, what you need to know when you do the root locus, the first thing for any system, you need to identify where are the poles, the zeros, this roughly random sketch. Then the next thing, identify the segments. Then after that, we need to identify the sigma A and phi A, the asymptotes and the asymptotes angle. For example, like this one will be centroid like this. Then you will say most likely it will go this way, and it will go this way. After that, we need to identify the k critical and the omega critical. Once you find all of those, we are done with the root locus so far. So thank you so much for that. And I'll keep in mind that root locus, we still have more topics about that. But since we are currently in the summer semester, that's all of what you need in root locus. However, in the future semesters, of course, there are more multiple steps, or we still need to do more steps than that. But for here, we will stop at this point in root locus. I will not go further, but as I said, in the future semesters, we will discuss more about, in future semesters, we will discuss more about root locus. So thank you so much for that. Then let's end the recording.